Hello, in this lecture we shall talk about the relationship between context-free grammars and other types of languages such as natural languages and programming languages. So, role of context-free grammars in natural languages and programming languages. Let's first see the role of context-free grammars in terms of natural languages. Let's try to create a sample context-free grammar for the English natural language. So sample CFG for legal, grammatically correct English sentences. Note that this is just a sample, so it will not provide the rules for the whole grammar. So a legal English sentence, let's denote it with S. This will be our starting variable. Can be expanded with, can consist of two main structures. One of them is, the first one is noun phrase followed by a verb phrase. Okay, and a noun phrase may consist of, again, different types of rules. We can have a determiner, basically one of the articles, the an, followed by a noun phrase itself, or it could be an adjective followed by a noun phrase, so a small cat, for instance, or adjective followed by simply a noun. We write in here in this rule adjective followed by noun phrase so that we may follow this with further nouns, with further adjectives. So big and ugly cats, let's say. So in that case we would need to expand this with adjective followed by noun phrase, and noun phrase would be expanded with yet another adjective and noun phrase. That would be adjective, adjective, noun phrase, so we could add further adjectives. As we said, determiner could be the a or an, and adjectives, let's just add some simple small number of adjectives to our language. So let's just say we have an adjective as big and an adjective as fat. We can add many others, and let's just say epsilon is also an adjective, so that when we construct a noun phrase, we can just simply have epsilon and simply have a noun as a noun phrase. And a noun, again, to make a simple grammar, let's just add some simple nouns. Mouse, for instance, cat, for instance, cake, for instance, and so on. And a verb phrase in here can be basically a verb followed by a noun phrase. So eats cake, for instance. Eats would be verb, noun phrase would be cake. And verb, let's just write some sample verbs that we could have in our grammar: eat, eats, so on. This is just a simple sample grammar for the English language. Okay, let's just try to derive a sample sentence using the rules of such a grammar. So let's say our simple sentence is the fat mouse eats cake. How could we derive such a sample sentence using our context-free grammar for the English language? So we will start with our starting variable s representing a sentence, a legal sentence according to the rules of this grammar, S, and we will do our first derivation, expand S with the first rule. Note that in this grammar, all these words denoted with uppercase letters correspond to our variables, the variables of our grammar. S is a variable, NP, VP, determiner, adjective, all these are our variables. And in this case, so far we have considered simpler grammars where our terminals were just simple symbols such as zeros or ones, or characters such as A's and B's. But in this case, in the case of a grammar for the natural language, we can have terminals that are words themselves. So the is a terminal, a, an, big, fat, mouse, cat, cake, eat, eats, all these are terminals. The terminals are denoted with lowercase letters. So let's start our derivation. We expand the starting variable S with the rule, noun phrase, verb phrase. We only have a single rule in this case. Let's try to do only leftmost derivations, where each time we try to expand the leftmost variable. In this case, we have two variables. At each derivation step, we will try to expand the leftmost variable, in this case NP. So to arrive at this sentence, what should we expand the variable NP with? We will expand it with the first rule, determiner followed by noun phrase, because we have a determiner followed by a noun. So determiner and noun phrase, and we already had the existing verb phrase. Next, we should expand the leftmost variable, determinal. In this case, it corresponds to initial the noun phrase followed by verb phrase. Next, we should expand this noun phrase variable. So what should we expand this noun phrase variable with? At the end of this noun phrase, we should arrive at fat mouse. So since we want to arrive at this, we can expand it with this rule that says the initial terminal the, and for noun phrase expand it with this rule, adjective followed by noun, and then existing verb phrase. Expand the leftmost variable adjective, so to arrive at this noun phrase, the fat mouse, we can expand adjective with our terminal fat, the fat followed by noun and verb phrase. Next, we need to expand this variable noun. In this case, we can expand variable noun with the terminal mouse, the fat mouse followed by our verb phrase. Next, the leftmost variable that remains is the verb phrase. What should we expand our verb phrase with? With the single rule that we have, verb followed by a noun. So the fat mouse, verb followed by noun. Next, we would need to expand this verb, which would be the fat mouse. In this case, our verb is eats, followed by noun phrase. Finally, we would need to expand our noun phrase with the fat mouse eats. Since we only need our noun cake, we can expand it with this rule, adjective followed by noun, adjective followed by noun. In the next derivation step, we would expand adjective with epsilon, don't put anything here, and noun would simply be expanded with cake. So we would arrive at the sentence, the fat mouse eats cake. Okay, so this was our first example. to discuss the relationship between context-free grammars and languages. In this example, we considered the relationship with the natural languages. Next, let's try to consider the same relationship between context-free grammars and programming languages. So now let's consider a sample grammar, a sample context-free grammar for a hypothetical programming language. For a programming language. Okay. Note that such CFGs exist for every programming language. So for instance, if you search on the internet for the Python reference, such a reference will basically consist of all the grammar rules that applies to the Python language. So in this example, we'll just consider a small portion of such a grammar where all the grammatical rules of a specific programming language is described. So again, let's say we are trying to consider the portion as it applies to simple statements in a hypothetical programming language. S is our starting variable corresponding to a statement in a programming language. So we could have if statements, while statements, and so on. We will just write a couple of them. A statement can be an if statement, which can be defined as follows: if, in parentheses, write an expression, some expression. This expression is denoted with the variable e, followed by, again, some other statement. In this case, S and E are our variables. What are our terminals? If is a terminal, left parenthesis, right parenthesis is a terminal. This is one of the rules. We can have if-else statements. So if parenthesis expression, execute some statement, else execute some statement. Else. So again, terminals are if, left parenthesis, right parenthesis, and the else keyword. Another rule could define the while statement, for instance. While expression is true, execute some statement s. Our terminals are while, left parenthesis, right parenthesis. E and s are our variables. So we could add further rules corresponding to the main constructs in our programming language. Let's just write down one last one. Return, let's say, expression e. Again, for this rule, our terminal is the return keyword. We need to give a definition for the rules of the expression e. So e, let's just give a very simple expression rules. So an expression may simply itself be a single number that's denoted with n. In this case, let's just limit our numbers to be just simply zeros or ones. Or an expression can be any combination of arithmetical operators or comparison operations. So an expression may be some expression plus another expression. It can be an expression minus some other expression, expression multiplied with another expression, expression divided by another expression, expression in parentheses, expression greater than expression, and so on. Okay. A very simple grammar for a hypothetical programming language. Again, in this case, our terminals are all these operators: plus, minus, multiplication, parenthesis, comparison operator, and so on. For the number variable, our terminals are zeros and ones. Let's try to do a leftmost derivation of a simple statement in this programming language. So a simple if statement could be as follows: if 0 plus 1 is greater than 0, then simply return 0. let's try to see how we can derive this simple statement in this programming language. So we start with our starting variable s, which corresponds to a statement. Since we only have an if statement, we can expand it with the rule corresponding to the if statement. Expand it with if, in parentheses, expression statements. Since we are doing a leftmost derivation, in the next derivation step, let's expand this expression. For this expression, let's first, we can use any one of these rules that would give rise to this specific expression 0 plus 1 greater than 0. Let's first use this addition expression. So if, in parentheses, expand e with e plus e, the rest remains the same. Let's do another derivation step. For the leftmost variable e, we can expand it with, or let's see. Let's assume that the first derivation was with the greater than sign, so e greater than e. In the next derivation step, to arrive at our 0 plus 1, we can expand this e with the rule e plus e. If e plus e is greater than e, then execute the statement s. For the next derivation step, to arrive at this e, we will expand e with simply being a number, which would be expanded with a 0. So if n plus e greater than e, and statement s, to expand n with a 0. If 0 plus e greater than e, then s. And then for the next derivation, expand the leftmost variable e. If 0 plus, again we expand it with the number, with this rule n greater than e, statement s. Expand this number variable with simply 1. If 0 plus 1 greater than e, statement s. Expand this e with, again, this rule number. If 0 plus 1 greater than number n, s. Expand the leftmost variable. If 0 plus 1, number simply being 0, greater than 0, then s. We need to do another derivation to expand this variable s. Since we simply want return s, we will expand it with this rule. If 0 plus 1 greater than 0, then return e. We need to do one final derivation. We need to expand this e. Since we just want to return a number, we can expand it with the rule that goes to the number. If 0 plus 1 greater than 0, return a number. One last derivation, and we will expand this number with simply 0. If 0 plus 1 greater than 0, return 0. Okay, now that we have talked about the relationship between context-free grammars and seen that they are useful in specifying, defining the grammars of both natural languages and programming languages, let's see an equivalent way of doing derivations. So far in the previous examples, we have done leftmost derivations where we start with the starting variable. At each derivation step, we expand the leftmost variable according to its rules, expansion rules. Let's talk about a visual way of representing this, which is the parse trees. So what is a parse tree? A parse tree is basically a tree where at the root of the tree, root is our starting variable, The internal nodes correspond to the variables of the grammar. Internal nodes nodes correspond to variables, and the terminals are represented at the leaves. So leaves are terminals of our grammar. If in our grammar, if there exists a rule in our grammar that says A can be expanded with some string alpha 1, alpha 2, all the way up to alpha k, such a rule in our tree corresponds to the following structure. A is a node in the tree, and then alpha 1 is leftmost child, alpha 2 next child, and so on, all the way up to alpha k, the rightmost child. And how do we define a derived string using parse trees? A derived string will correspond to all leaves. Remember that leaves correspond to our terminals. All leaves read from left to right. From left to right. Let's just give a simple example. So, for instance, let's consider a very simple context-free grammar to define expressions in programming languages. Expression, to make it simple, an expression can simply be a number 0, a number 1, or it can be the addition operation, or it can be the multiplication operation. Okay. Given this simple grammar, let's try to see how a sample string can be derived using parse trees. So let's just give the following string, w equals 0 plus 1 times 1. So if we consider this simple string, the root should be our starting variable. In this case, our starting variable is e. Next, we should expand e with one of the rules that corresponds to it. Since we want to arrive at this expression, 0 plus 1 times 1, we can expand e with either this rule or this rule. Let's say first with this one, e can be expanded with e plus e. Okay. Note that since the terminals in here are 0, 1, plus, and multiplication sign, we arrived at plus in here. This will be a leaf node. It will not be expanded further. In the parse tree, we expand only the variables. So if you want to expand this e in the next level, since we want to arrive at this expression, we can expand e with simply the number 0. For this e, we can expand it with e times e, since we want to arrive at 1 times 1. So e, terminal multiplication sign, and e. For this e, we can simply expand it with the number 1. For this e, we can expand it with number 1. If you read the terminals, which are at the leaf level from left to right, so 0, plus sign, 1, multiplication sign, finally another one, 0 plus 1 times 1. So reading the leaves from left to right gives us our string generated by this grammar. We could do the same thing using our leftmost derivations as well. Note that one thing we mentioned earlier was that for this string, we didn't have to expand at the beginning with the rule e plus e. We could expand initially with the multiplication as well. Let's see that parse tree. It will be take e as our starting variable, and then next expand it with the following rule, e times e. Okay. To arrive at this string, this left e can be expanded with the addition rule, so e plus e, e plus e, and this e would be expanded with simply the number 0. This e would be expanded with simply the number 1, and this e would simply expand it with the number 1. Okay. Again, let's check the leaves of this parse tree from left to right, 0 plus 1 times 1. 0 plus 1 times 1. Okay. In this example, we can see that both of these parse trees gives rise to the same string. Okay. Let's do another example string. Let's try to derive another example string. So let's say our string is, this time let's just simply say 0 plus 1 plus 1. Again, we should be able to see that we can construct two separate parse trees corresponding to the string as well. So our first subtree, the root is e expanded with addition, e plus e. To expand this e, we can choose to expand it directly with the rule that goes to 0, 0. And to expand the rest, then e, this e would be expanded with yet another e plus e. E would be 1, sorry, and then e would be expanded with 1. So reading the leaves from left to right, 0 plus 1 plus 1, which would be this string. But yet another parse tree for the same string would be, again, expand initial e with e plus e, but this time for this e, we can expand it with, instead of simply 0, we can expand it so that it will give rise to the string 0 plus 1. To do this, we can expand it with e plus e, e going to 0, e going to 1. So now we have 0 plus 1, and e would give us 1. Again, reading the leaves from left to right, 0 plus 1 plus 1, which is the same string. So in both examples, we can see that we can have multiple parse trees for the same string. Okay? And the parse trees, they are useful for showing us the order of deriving a string. And if a string consists of operators like addition, multiplication, and so on, it tells us, each parse tree tells us the order of doing these operations. So for instance, if we, for this example, 0 plus 1 times 1, this parse tree tells us that we first do the multiplication operation and then do the addition operation. So we first multiply 1 and then add 0 to the result. Whereas in this parse tree, in the second parse tree, we first execute the addition operation and then the multiplication operation. According to this parse tree, we first execute 0 plus 1, afterwards we multiply it with 1. Same goes to this example as well. So this left parse tree first executes 1 plus 1 and then adds 0 to the result, whereas this right parse tree first executes 0 plus 1 and then adds 1. Since each of these parse trees tells us about the order to execute these operations, the parse tree that we choose will obviously be important. Okay, because there could be cases where left parse tree gives a different result than the right parse tree. Okay. So we will define such grammars as ambiguous. Let's define an ambiguous grammar. A grammar G is ambiguous if there is some string inside the language of the grammar so that there exists more than one parse tree for that string. So a grammar G is ambiguous if there exists a string W in the language of the grammar such that there exists at least two different parse trees, or note that we don't have to define parsing in terms of simply parse trees, we can define our derivations in terms of leftmost derivations as well. If there exists at least two different leftmost derivations, if there exists at least two parse trees, then we call for deriving the string w, for w, then we call the grammar G as ambiguous. If we give an ambiguous sentence example, the same thing may arise in natural languages as well. So for example, consider the following sentence. He said on Sunday we would go to the park. Now consider the meaning of this sentence, because to which phrase should we apply this word combination on Sunday? So we could apply it to this phrase, he said on Sunday. So when did he say this sentence? He said it on Sunday. So this is one interpretation. A second interpretation is to apply this word combination to the second phrase, to this one. So he said we would go to the park on Sunday. When would we go to the park? We would go to the park on Sunday. So we can see that for such a sentence, depending on how we do the derivations with respect to the rules of the grammar, this sentence may have two separate interpretations. Okay. So this is problematic in natural languages, but you should be able to see that this would be even more problematic in terms of programming languages. So if a programming language were to have an ambiguous grammar, then if somebody writes a program, let's say if somebody writes a statement, that statement could be legal according to the rules of the grammar of that programming language, but since there would be two or more interpretations of the same statement, two or more different results could be provided as the output of the program. Okay? This is not desirable. It should be obvious that this is not something that we want. So if there is some grammar, some context-free grammar defining some language, it's desirable to have that grammar to be unambiguous. Let's see how we can make the previous ambiguous grammar, how we can turn it into an unambiguous grammar. So remember, the previous grammar was to make previous grammar unambiguous. It was expression can be simply a number 0 or 1 or e plus e, e times e. To make such a grammar unambiguous, we need to decide on two things. Okay, so what was the problem with, let's see, the sample parse trees that we had from the previous grammar? One string was of this form. Okay, such a string could give rise to more than two parse trees or more than two leftmost derivations, which makes the grammar ambiguous. The problem in here is that when we investigate these two parse trees, the difference between them is the order of doing multiplication versus the addition operation. Okay, so to make such a grammar unambiguous, one thing that we should decide is the precedence rules that we want to apply. The left parse tree, for instance, gives more precedence to multiplication, whereas the right parse tree gives more precedence to addition operation. But this is not the only problem. As we can see from the second sample string, we also, in addition, need to decide on associativity rules. Do we execute the same types of operations going from left to right or going from right to left? So for instance, this parse tree in here applies right associativity. It first executes the rightmost addition and then executes towards left. Whereas this parse tree applies left associativity. It first executes the left addition and then goes on towards right. It executes the next one. According to the normal arithmetic rules that we have from these parse trees in terms of precedence rules, this one should be applicable, this one should be applied, which means that multiplication has higher precedence than addition. And in terms of associativity, this one should be the right one because we want to apply left associativity for the same types of operations. So, can we modify this grammar such that we will have our precedence rules implemented within the grammar so that multiplication has higher precedence than addition. And also, in terms of associativity, we want to be able to apply left associativity so that if we have, for instance, a plus b plus c, we first execute a plus b, then we execute the result, then we add the result with c. Okay? Whereas the right associativity would first add b plus c and then do the next addition. Okay? Although, in terms of the simple grammar, which includes only multiplication and addition, associativity may not seem to be a problem, but imagine having the other operations as well, such as subtraction and so on. For instance, we could have different results if I want to implement the execution of this expression for minus 7 plus 12. With the left associativity, this would give me minus 3 plus 12, which is 9. With the right associativity, I would have 7 plus 12, which is 19, 4 minus 19, which is minus 15. So we can see that again, left associativity will in general, implementing the associativity rules in general will be important. So how can we fix such a grammar so that we apply these two rules? So to be able to implement this precedence rules, we will need to introduce new variables for higher precedence operations, and to implement the type of associativity that we want to impose, we will need to be careful about the order of variables in our rules. So these will be the two main ideas. For precedence rules, as we said before, we need new variables. So we will introduce first a new variable I corresponding only to our numbers, because simply numbers have actually the highest precedence. So I can be 0 or 1. The next higher precedence should be applied to multiplication, so we will introduce a new variable corresponding to our multiplication operations. Let's denote that variable with t. T can itself be simply an I, can simply be a number, 0 or 1, or it will be t, and t corresponds, by the way, to a term. It can be a term multiplied with a number. Okay? So basically, a term t will correspond to an expression that only consists of multiplication operation. Okay, so t could, for instance, correspond to 0 times 1 times 1 times 0 and so on. An expression only consisting of multiplication operations. Finally, we can give now the rules for the expression itself, e. An expression can consist only of multiplication operations. In that case, an expression may simply consist of t, okay, or it will be a combination of multiplication operations, a combination of a term, and addition operation. So to do this, we write down the addition operation as take an expression, addition operation, and a term. Okay. Let's take this grammar and let's try to see our previously the strings, the derivation of the strings in our previously grammar. So let's rewrite our unambiguous grammar. So our ambiguous grammar, ambiguous one is expression 0, 1, expression plus e, expression times e, and unambiguous version was identifier 0 or 1, and then term, which could be simply an identifier, or term multiplied with identifier, and expression may simply be a term or an expression plus a term. Okay, let's see the previous, how this unambiguous grammar derives the previous strings. Our first string was w equals 0 plus 1 times 1. Remember, for this string we could have different derivations with this grammar. With this grammar we may first execute plus and then execute multiplication, or we can also do the following: first execute the multiplication and then execute the addition operation with respect to this grammar. However, we will see that this unambiguous grammar will not allow us to do more than one derivation. It will allow us only to do a single derivation, which will be the correct derivation with respect to the rules of precedence. It should allow us only to do the following operation: first do the multiplication and then do the addition. Let's see if that is the case. We start with our starting variable. Our starting variable is still e, by the way. We start with e. We need to do a first derivation step. Now, we have the chance to expand e with this rule t or e plus t. If we were to expand e with t, remember that t can be a number or it can be a bunch of multiplication operations followed by each other. Okay, a bunch of multiplication operations. So this means that we cannot simply expand e with this rule t, because in our expression we have a plus sign. T doesn't give rise to any plus sign existing in its expansions, which means that we have to expand the initial e with the second rule, e plus t. E plus t. Have to do this expansion. We cannot expand e with t because otherwise we cannot arrive at this string. Okay, let's do our usual leftmost derivation. What can we expand this leftmost variable e with? So e plus t. Remember, we want to arrive at this string, and which means that this plus sign corresponds to this plus sign, which means t must be 1 times 1 and e in here must be 0. Okay, so this means that we cannot expand this e with e plus t. We can only expand it with t plus t. So note that in this derivation step, among the multiple alternative rules that we can choose, again we have to choose exactly one of them. So we have to expand e with the rule going to t in this step as well. Okay, for leftmost derivation, how could we expand this t? We have now t plus t. T must definitely go to 0. So again, we cannot use this rule. Instead, we need to expand t with number I plus t. I is expanded with 0, 0 plus t. Each of these steps, we have to choose the rule that is specified in the derivation step. Let's continue. 0 for 0 plus t, what should we expand t with? Since it should correspond to 1 times 1, it should be this rule. It cannot again be this rule. 0 plus t times I. What should we expand t with? We should expand t with the number I. 0 plus I times t. I should be expanded with 0 plus 1 times t. Finally, t should be expanded with the rule I. 0 plus 1 times I should be expanded with the number 1. Note that in this leftmost derivation sequence, each of the derivations that we do are a result of obligations. Okay, so in this case, for instance, to choose among the rules to expand the variable e with, we can only choose one of the rules among the many alternatives. At each step, this is the case. We have to choose exactly one rule to arrive at our target string. Okay? If the grammar were not unambiguous, this wouldn't be true. We could have multiple choices to do. Let's see, this string was relevant with respect to how we apply the precedence rules. We can see that according to these derivation sequence, the multiplication operation has more precedence than over the addition operation. It can be seen from this derivation step as well. Let's see our second string, which is relevant with respect to the associativity rules. 0 plus 1 plus 1. Let's see how we can arrive at this string. Again, start with the starting variable e. We have 0 plus 1 plus 1. Again, we cannot expand e with this t because t only has the multiplication operation, whereas we have addition operations. So we have to expand it with e plus t. For expanding the leftmost variable e, again, we cannot choose simply t because t would give multiplication or a single number, and this t also the same, so we couldn't have two addition operations. So we have to again expand it with e plus t plus the previous t. Okay, so e is expanded with e plus t. Finally, how do we expand this leftmost variable e with? Since we want to arrive at 0 plus 1 plus 1, e will be expanded with the term, with this one, the previously existing terms. This leftmost t will be expanded with a number I plus t. This I would be expanded with simply 0 plus t. Leftmost variable t would be expanded with the number 1, 0 plus I plus t, 0 plus 1 plus t. Sorry, this one is expanded. And finally, to expand this t, 0 plus 1 plus I, and I is expanded with 0 plus 1 plus 1. Again, if you check the derivation steps, you should be able to convince yourself that for this string in our derivations, when we choose our rules to expand, we don't have more than one alternative at any step. We exactly have one alternative to do our expansion.